Hey everybody, how's it going today? This week we'll be starting our unit on stoichiometry, but before we get too far into problems and calculations, there are some new ideas we need to discuss. Today we will be learning about moles, unit conversions, and common units used in chemistry. There will be a practice video that will cover unit conversions in a bit of extra detail if you find it confusing, but let's get started by looking at a type of problem actual chemists face regularly. Let's say you're a chemist that has been tasked with isolating some solid copper from a solution of copper chloride. Since you are so knowledgeable about single replacement reactions and the reactivity series of metals from last unit, you know that placing aluminum foil into copper chloride solution will result in the formation of solid copper. Unfortunately, you only have 6 grams of aluminum. How much copper could you isolate from your copper chloride solution, and how much solution should you use? Now, we can start approaching this problem by looking at the chemical equation, which is certainly helpful. The chemical equation for this reaction is Al plus CuCl2 yields Cu plus AlCl2. This tells us there is a 1-to-1 ratio between aluminum and copper, but there's a bit of an issue here. This 1-to-1 ratio is a ratio of atoms. Remember that chemical equations tell you the number of each type of atom or molecule present in a reaction and tell you nothing about mass or volume. At the moment, we don't have the tools to actually solve this problem. Here's why. We can't measure out individual atoms or molecules of our substances, and we can't measure masses in AMU. Remember that the atomic mass of different elements tells us their mass in atomic mass units, or approximately the mass of protons plus neutrons. Since normal scales only go out to the tenths or hundredths place in grams, we can't come anywhere close to weighing out something on that small of a scale. And I don't know about you, but I can't see individual atoms or molecules of a substance. As such, we need to do some unit conversions to be able to measure our substances at a scale that is useful to us. But how can we convert atomic mass units into grams or single atoms into a volume? Enter the mole. Not that kind of mole, though it is adorable. The mole, spelled M-O-L-E, but often written as a unit as simply M-O-L, is an important unit in chemistry. If you think the word looks like a shortened version of molecule, you've got a good eye, as moles do in fact measure the number of molecules, or atoms, in a sample of a substance. Specifically, 1 mole equals 6.02 times 10 to the 23rd molecules or atoms. You might remember that number as something that was referenced during our scientific notation unit, and you might want to brush back up on using scientific notation, because we'll be using this number a lot. Let's talk a bit about Avogadros number. In spite of the bad avocado joke, it can be a helpful tool for remembering 6.02 times 10 to the 23rd. So if you refer to it as Avogadros number, I won't be too upset. Avogadros number may seem obscenely large, and possibly even arbitrary, but is actually a very useful number for converting chemical units. The main reason is this. 1 mole of a substance will have its atomic mass in grams. That means that if you have 1 mole of hydrogen atoms, you'll have about 1.008 grams of hydrogen. As we'll see in the next video, this allows us to convert masses into moles or molecules so that we can do calculations with our chemical equations. But for now, let's instead look at a convoluted real-world problem that shows the importance of unit conversions. Let's say you're a fruit vendor who is taking inventory of your stock. Your suppliers are all out to get you, so each one sells their fruit to you in different quantities with different units of measurement. You get your apples in mass units, specifically by the kilogram, as apparently you're also a fruit vendor in a country that uses a reasonable system of measurement instead of pounds. Sorry, imperial system. Your pears come by the cubic centimeter, which is a measurement of volume, and your oranges come by the dozen, which seems the most reasonable unit of measurement in this case, but I don't really know much about the fruit selling business. You order 2 kilograms of apples, 5,900 cubic centimeters of pears, and 2 dozen oranges. How much fruit do you have in total? Now, one way to solve this problem could be to wait until your shipments get in and simply count the number of each fruit. But let's say that you're trying to make sure you'll be able to meet your demand for the week, so you need to know ahead of time how much of each fruit you'll have. Oranges are easy. You have 2 dozen. Each dozen contains 12 oranges, so you're left with 24 oranges. Apples and pears won't be quite so easy. For apples, you'll need to know the average mass of an apple, which, based on a quick Google search, is about 100 grams. If you ordered 2 kilograms, or 2,000 grams, and there is 1 apple per 100 grams, you can calculate that you will end up with about 20 apples. Now, for pears, you would need to take the average volume of a pear, which is apparently 236 cubic centimeters, and use that to convert your total volume to a number of pears. Assuming for perfect packaging, your 5,900 cubic centimeter order divided by the 236 cubic centimeters per individual pear leaves you with 25 pears in total. That means that in all, you will have 20 apples, 25 pears, and 24 oranges. Now, we'll get a lot of practice using these unit conversions and things before we actually get around to doing any big problems with our stoichiometry unit, so don't get too panicked if that was a little bit confusing. All of this talk about fruit might seem a bit unrelated to chemistry, but the same principles we just had to apply in the previous problem are the principles we have to use in chemical reactions. Moles are a measurement of number, and we use moles the same way we use molecules, in terms of ratios. Since our original problem, with aluminum and copper, called for a 1-to-1 ratio of molecules, we can use a 1-to-1 ratio of moles, and everything will work out properly. Your chemicals won't be measured directly in moles, however, so you'll need to convert between units to get to moles before you can actually apply stoichiometry. We'll look at the specifics of how to convert different measurements to moles in future videos, but it's worth identifying what those units are. Usually, with a solid substance, we take our measurements in mass. For us, that means grams. For gases, we have to use volume to measure gas, and it gets a little bit complicated as we explore the properties of gases relative to temperature and pressure. Lastly, liquid and aqueous substances can be measured in either volume or mass. The volume is the more traditional method. This week, we will look at the unit conversions for solids and gases. Let's take a brief moment to summarize everything from this lecture. Chemical equations tell us the ratio of chemicals relative to each other, but are measured in atoms or molecules. We don't have the ability to measure out individual molecules, so we instead need to use unit conversions. A mole is a unit that measures the number of molecules, but at a scale that we can actually use. 1 mole is equal to 6.02 times 10 to the 23rd, which is Avogadros number. And moles can be used to convert measurements typical of reactants, which are usually mass or volume, into units that can be used directly in a chemical equation. That's it for this video lecture, and I'll see you guys next time.